Okay, I was going to start. If the AV guy can push the slides up to the monitor. Right. Okay, guys. Thanks for coming. This one's going to be about microservices. I assume you know that. If not, you're in the wrong room. My usual policy is if you do not feel you are learning anything, please feel free to leave. I won't be offended. Right. Nothing really important on this. I'm Ian Cooper, by the way, for those who's seen me talk before. Most of you? Some of you? Okay. Most of this is really unimportant. It says that I'm old and I have grown my beard. The most important part is just because I'm standing here doesn't mean that I am necessarily any smarter than any of you. I'm just mouthy. Okay, and that's where I work at Huddle. Please don't use SharePoint, just use us instead. Right. We're going to talk about it. So I'm going to talk about microservices, and I'm going to talk about it in the context of a number of things. The first thing is I'm going to talk about why you might want to think about using microservices, and I'm going to talk about that in terms of managing complexity. Why might it come in? Then I'll give you an overview of how you might choose to implement microservices. What would it mean to do that? And then I may talk to you about breaking up a monolith, the assumption being that many of you will be in a situation where you're taking a monolithic application and choosing to break that up into a series of microservices. And we'll finally talk a little bit about the idea of operating microservices. This is quite a lot to cover in 1 hour, so some of it will be necessarily high level. Has anyone today think they're building something that is a microservice architecture? Okay, a few of you. Have any of you built SOA architectures? Okay, some more of you. Anyone built component architectures, DCOM, Corba, that kind of thing? Any of you old enough to have done that stuff? Okay, all right, great. So some of those things are kind of related. When we kind of start out building software, you can generally start an average kind of project with kind of one guy, and he starts writing some code. And generally, if it's a small enough problem that you're solving, you don't really need any structure, right? I could just write 400 lines of code, one line after the other in some big giant main routine. And if that's all it did, then that's probably a good enough approach. I don't need to add lots of software engineering to cope with that kind of scale. And as we begin to add more lines of code, because the domain problem we're trying to solve is more complex, we want more features as part of our product, we add lines of code. And as we add lines of code, it becomes increasingly difficult to cope with the model of saying, hey, here's just a whole ream of lines of code. So some of you may be old enough to remember the days when you get your computer magazine and you'd carefully type in every single long line basically to create your program for your computer game or whatever. And after a while, after a certain number of pages of code, that becomes quite tricky. And so at a certain point, you think, well, I'm going to need some structure. Okay. And that structure begins to increase, and also the other thing you begin to do is potentially consider that this one individual is no longer possible for you to really meet the deadlines that the business may have simply coding away on your own, and you're a risk. The bus might hit you, you might die. That's not good for the business, not good for you either. And so what you might want to do instead is add members to the team, right? And we know that I don't know if you know, but most of the research says the ideal way of building software is 4 guys in a room with a whiteboard. All other processes are really an attempt to try and scale beyond 4 guys with a whiteboard because that's the optimal. So we may go to 4 guys in a room with a whiteboard, maybe be really bashing out the software. And eventually we might even increase the team size up to about 2 pizzas. 2 pizzas seems to be roughly the limit of a size for a team. That's 2 American pizzas. That's quite a large number of people. That's about 12. Not 2 European pizzas, which obviously is a much smaller team. But yeah, so the idea is that you're going to increase the people. As you increase the number of people, you obviously need slightly more structure. It's very difficult for us to all work on code, which is just one long procedure, and the number of lines of code gives us a problem. The other thing is that there's a limit to what you and I can deal with in terms of the numbers of lines of code. So everyone kind of knows this idea that programmers, what they do is they create kind of a model in their head, they load up the software into an internal representation. This is why you shouldn't keep interrupting them, because you keep tearing down the model. When they've got that model in their head, they can actually try and modify, work with that program, add new features. And generally, the estimate is that about 35 to 50K lines of code, that's your limit. Okay, you can't really conceptualize more than that. As you get older, like me, and you've drunk too much beer, it's down towards the 35,000 lines of code, slightly more. Some of the youngsters are probably may actually be able to push up to 60 or 70. You know, they're fresh and they haven't destroyed too many brain cells yet. So there's kind of an upper limit, really, on what you can deal with in terms of an individual or a team and size of code. But as we go up this stack, one of the things we can do is, as we need to increase team size, as we go up from a few hundred lines of code up towards this 50,000 number, we can use a standard set of approaches to managing the complexity of our software. And while this may seem like, where is he going with this? This doesn't straight to microservices. Please bear with me and we'll work through it. A slight tangent. Who's ever read this or knows what this is about? Anybody? A couple of people, right. Who's read Fielding's paper on REST? Okay, a few more of you. So Fielding's REST paper on REST, everyone reads basically parts 5 and 6. Parts 5 and 6 describe REST. Parts 1 to 4 are about architectural styles. So back at Carnegie Mellon University in the 90s, Mary Shaw and David Garland produced this notion of architectural styles. And the idea really says, well, if we're going to have architectures, we ought to be able to try and compare them. Because then we may know which architectures are the best solutions, which kind of problems. So they created this notion of an architectural style, which is analogous to kind of a design pattern in actual writing code, and said we can describe architectures in terms of a sort of standard language, and then we will be able to compare them and talk about them. And REST is just an architectural style. CQRS is an architectural style. Okay. So an architectural style tends to consist of a number of things. It consists of a component that's basically state and behavior. And it consists of a connector, how two components talk to each other. And generally, we describe the components as having a role, client-server. And the port is kind of in this notion of where the component meets the connector. And the idea is we can determine a series of invariants and constraints, which you have to have for a particular architectural style for both components and connectors. You can say, to be using this architectural style, your component must be X, and your connector must be Y. And that allows us to predict certain properties that an architecture that has that style will be. So REST, if you go and read Fielding's paper, you'll see essentially a description of the invariants and constraints that make you RESTful, and therefore predictably what the properties are. If you choose to omit some of the invariants or constraints, it's less easy to predict what the properties are. Right? That's what we're really saying. Styles are heterogeneous, turtles all the way down. So the idea is that a given component may itself be another architectural style. Okay? Why is this useful? So we can begin to talk about the properties of certain types of approaches we use to modeling software. So the first thing we would tend to do, if we start expanding our code beyond about 400 or 500 lines, is start thinking, well, okay, then we need to break this problem down. So I'll break this problem down procedurally might be a really good starting place. You know, procedural code is still a pretty good way of structuring stuff. You know, Linux is built out of procedural code. And so we might say, well, okay, what we're going to do is decompose our problem into a number of pieces. Inside each of those functions or subroutines that basically we will create, so a subroutine is a component, we'll say, I'll take a piece of the functionality, I'll abstract it behind this function call. I no longer have to understand the implementation details of that function. I can simply understand that if I call it, it gives me some kind of level of service, which I will then basically be able to think about as a smaller unit. So I'm beginning to make the problem of dealing with lines of code easier because I can reason about this unit of functionality, this function. Okay. So it's decomposed, and essentially the other thing that's useful about them is that they tend to be some kind of decoupling, right? So the things inside that function body aren't necessarily exposed outside it, and therefore I begin to start decoupling myself from the complexity that they may be internal. So if I have a routine for calculating the price of shipping between Oslo and London, I can put it inside a function, and other parts of my software don't care about changes to that particular routine. Right? If I choose to change my shipping algorithm, the other parts of my application shouldn't or don't need to care. And that's main and subroutine. It's fairly efficient, it's intuitive. The idea of breaking a problem into parts is a very intuitive way for us to solve problems, and it's fairly easy to follow. Right? Main and subroutine is for most of us is a pretty straightforward. If we see a program written like that, we can fairly easily interpret it. There are some issues. One of the chief ones is really that data lives globally, and we just basically operate on data globally, and that causes problems. We are all coupled to this global data representation. When it changes, it has ripples effect out on the software. Okay. But the key principles that we're using to try and manage complexity are decomposition, break a large problem into smaller parts, and loose coupling, try to essentially prevent ourselves from depending on implementation details. Okay. If we get to the point we can't read it, I will zoom in on some of these, because some of these slides get a bit dense, and I'll keep an eye on it, shout out. Okay. Mains and subroutines get us a certain amount of distance, but after a while we get a huge number of functions, and it's very difficult to understand, is there a function that does X, where does it live? You end up with people duplicating subroutines because they don't know that someone's already written that subroutine and it exists on another part of the software. And so we need some kind of greater organizing principle, and that's where the hierarchical architectural style comes in, which layering is one of the most common approaches. CQRS is just an example of a hierarchical architectural style as well, for example. Okay, so what we do when we say basically we want to create a layered style, well, we say let's take a collection of things that probably change together, a set of subroutines that deal with a common problem and probably have a single force of change behind them, so a whole lot of my functions that deal with my shipping out cost algorithm, and put them behind a stable interface that is much more coarse-grained than the problem inside. So essentially I'm doing the same thing I did with a function. I'm taking decomposing the problem, taking a section of it, which is now basically probably my subroutines, collecting them behind an abstraction and saying now the programmer only has to reason about the abstraction of the layer boundary and doesn't have to reason about the internal details. So now he knows that he's calling the shipping layer and doesn't have to worry about the details. By the way, classically when you see lots of diagrams of layers, you'll see presentation, business logic, data access. That's an example of a layered architecture, but layered architectures do not define what those layers are. You can have as many layers as make sense to you in an application. All right. There are some constraints on layers, so essentially you provide services, and so a layer above you can call you, but you can't essentially call the layer above you. That's to prevent circular dependencies, which are hard to break. You can use callbacks if you basically need to solve that problem particularly. And the idea is that some nice properties about that. Abstraction helps us reason about things. I need to know about, there's a shipping layer, there's a data access layer, there's a layer for, I don't know, insurance rate calculation. I can do all those kind of things separately. Highly cohesive, that's very useful. So when we talk about loose coupling, the other side of it is cohesion. So I can make things very loosely coupled, but I can end up in a situation called shotgun surgery, where essentially I have to go to large numbers of places in my code, which are all very distinct from each other, to change something. If my shipping algorithm is cascaded across functions which are in just a random collection of files all across the code base, it's quite difficult quite often for me to figure out where that is. And people end up with recipe sheets pinned to kind of walls. If you want to change X or add one of these, you have to follow these 14 steps and go and change all these places. A bit rubbish. Have a nice little layer where you decompose the problem into, right? Nicely coupled and quite testable. So in the sense that essentially I can begin to write tests at layer boundaries, think about the idea that essentially I don't need to understand the implementation details, because if I couple my test to my implementation details, it makes it very hard to change my software without having been forced to change my tests, right? So it's early notions of kind of refactoring creep in. Generally what the connections are is just, both of these last cases, just an in-memory procedure call. Disadvantage is layer boundaries becomes a bit of constraint. You want to actually sometimes jump a boundary, but it's okay. All right, so we're adding a new principle to the ones we talked about with basically decomposing to main and subroutines. We're saying, well, we want to basically decompose a large problem to smaller parts. We want to basically be loosely coupled. We want to essentially have an abstraction and encapsulate information behind it. And we want to be cohesive. So we'd like to actually now say, well, we'd like to basically, behind some kind of stable interface, have a collection of things that all change together so that they can be dealt with as a unit quite easily, reduce our complexity. Okay, objects. How's that doing? Is that still, that's probably readable still? Okay. So the next one down the line is object orientation, right? So object orientation comes around because we decide that this problem that we've still not basically addressed around shared data, which essentially means if I change my data structures, that ripples out everywhere. Well, we could address that too, right? So we could actually decide that in create an object, And inside that object, we'll have both behavior and state, and we'll hide the implementation details of from the consumer, and they'll just basically see the public API that you can talk to. And essentially, there's a usual path, which is procedural abstract data types, which essentially say there's a way of hiding our data from callers by using kind of modularity or language features, and it ends up as object orientation. Objects tend to be dynamic in the sense that you can replace at runtime one object for another by using some kind of abstraction. Polymorphism is an example of that behavior. So I can say, well, you may think that you're calling interface A, but actually what I'm going to give you is either implementation B or C. Okay? They have a set of invariants that they have to basically preserve. So the idea is that objects should be in a consistent state after an operation. So some invariants are true before, I operate on it, and at the end, my set of invariants are true again. So I can predict the state of an object after calling an operation. And they're encapsulated. So again, some nice properties, very similar to layers. Things we talked about before, we're decoupled, we're decomposed, highly testable, and very cohesive, and generally use procedure calls to move between us. Okay. So the only thing we've really added to these general principles we're saying that we use for decomposing complexity in software is we're basically saying, well, we do loose coupling of details and state instead of basically just the behavior. Okay. So the assertion I make is that kind of covers you a lot of those patterns. If you're building with kind of a single team, 4 or 5 guys, your level of the number of lines of code to solve your problem is out to about 35 to 50K. You can generally build a software solution using only those techniques. Okay? You don't need to be reaching for the next set of techniques we're going to show you. Okay? So people ask, when should you use microservices? Not in the prior situation. What you need to do is be in a position where you start to cross this threshold. So you start to have more than 50,000 lines of code, and anything up to about, when you get to about 1 million, you've got extremely complex software, and I don't know that even microservices really help you manage that scale. But you also potentially begin to want to have multiple teams. And as soon as I introduce multiple teams, I introduce the problem that these teams probably want to work independently of each other. They probably want to have their own Scrum, they probably want to have their own Kanban board, etc., and they want to be able to release without constantly having to negotiate with the other team over who's got this file locked and why are you making changes to these files, we're making changes to these files. And so if the team is working on a single shared code base, they tend to get each other's way quite a lot, get annoyed, you get rows and arguments. And you get blame. This team has stopped us from actually releasing our software as we committed to this iteration because they made some sweeping global change and all sorts of problems, right? So you generally, the move towards multiple teams because you have that demand for features, then the move beyond a certain number of lines of code pushes you to the point where you think, okay, I've got to change my strategy. Okay. And really, the major route we use is a strategy of breaking our software up into components. Okay? So microservices are really just a component strategy, and they're an evolution of a number of approaches we've used to breaking software up into components. And by component, we essentially, in this particular context, mean a releasable kind of unit of software. Okay, so is that still readable? How's that at the back? Do I need to zoom it a bit for you so you can read that boxes? You okay? Okay, cool. Right. So we get a component. A component's kind of taking this idea of object orientation to the next level. Okay, it says, well, we could have this idea of some kind of object that has a coarse-grained interface and encapsulates behind it something else, right? It's going to look like an object. And maybe what it encapsulates behind it are just more objects, but it may have some state of its own, etc. And we say basically it's got a well-defined interface, which is like a layer, so it's got a stable contract with the rest of the world because we're going to expose it to public API. I want that to be stable and long-lived, not changing all the time because we're exposing it elsewhere. And we basically say there's two kind of ideas. There's a server and a client. Now, generally, the idea behind components was this kind of language and platform transparency. So the idea was, I will say, call my, I would say, right, what I need is a new shipping component. I'm going to call that, and I'm going to use that to calculate my shipping cost between London and Oslo. And the idea was this notion that the programmer shouldn't really care where this object lived. He should be able to ask some kind of broker for an instance of a shipping object, and then just make calls to it directly as though it was a local object he'd instantiated. Okay. And so we had request brokers like Corba, with COB runtime, and DCOM was a pain in most of our lives. And the idea was that you would say, I'm going to call this object, and it will do the work for me. And I don't really care where it lives. .NET Remoting is another example, JMI, they will do the same thing. And maybe I will have to do something interesting about lifetime management and actually saying to the server, well, is this going to persist between calls because it's hard to start up, so you get some kind of singleton notion, or is it going to be create a new one for each call, that kind of thing. And so this idea came of components. And components had some quite nice properties. You know, were highly decoupled, were highly decomposed, were cohesive. But the other nice thing was, because essentially these are releasable units, my teams could now work independently. This team owns this component, and it can release quite independently of other teams. Now, it may be that this is a kind of library that's hosted by a given runtime, or it may be that's a process in its own right. But generally, these things can be worked on quite independently, and because there's a stable interface, you can go away and, provided you don't change that interface, create new versions that optimize the shipping algorithm. I don't care. You just basically release it. I ask the broker for the object. I get your new version. That's very useful because we begin to break away from the problem that these two teams are now working against each other. Provided the two teams are working on separate components, we can begin to think about scaling our development process. We can actually say we can move beyond 12 people now. We can have 24 people. We can have 4 teams of 6, and we can divide our landscape up amongst various components that those teams will all then manage. Okay. And generally, the process we used to call between them was RPC. There is some messaging, Comp Plus, but mostly we're talking about RPC. So a remote procedure call just says, hey, you know how we can make procedure calls across the stack? Let's do one of those remotely. So from the programmer's point of view, you're just basically calling a method and passing the parameters across, right? And we used to have this thing called IDL, interface definition language. And the idea behind that is I'll define this interface in something like IDL, and then essentially I can actually provide implementations in a whole range of languages, right? So my .NET client can call my Java server because essentially they share some kind of IDL which allows us to actually define how that works. Right, and a very common thing back in the day I used to do a lot of was VB calling COM. Okay. And again, very useful. I can now have multiple languages. I can choose languages that are appropriate to the problem at hand. You know, there's a very common solution back in the day to have C++ components called by VB front ends because VB was very good at writing those front ends very efficiently in enterprise, but they wanted C++ on the back end for, say, their shipping algorithm. Okay. And so it's a nice property that we can actually be polyglot in terms of languages. Okay. There's kind of a problem. There's some problems, though, that emerged. One of the key problems we mentioned here is that this thing is still exposed to the fallacies of distributed computing. So when I make a call to this object that I've asked from my request broker, the problem is that call will fail over time because the network's not reliable. And so I'll make a call to the other object, and actually what I'm going to get back is a network error. Now, I don't really expect that. If I'm saying, I don't know where this object lives, I'm going to call it as though it were a local object. Local objects don't return network errors. They don't say, I'm busy, I'm holding too many requests right now, can you call me back later? So this notion that the programmer didn't have to be aware that they were making remote calls was a problem. The other thing was, you've got no notion essentially there of the fact that you are making a remote call quite often. And let's say, for example, that I'm in the middle of a database transaction that I'm holding open, and I decide to make a remote call out to another object. I'm now holding my database transaction open while I'm making a highly latent call to a different object, and maybe I'm living on a different server. So that became a genuine problem where people began to say, okay, this notion of location transparency is not what we want. So key changes to our principles. We've got decomposition and loose coupling still. We've got cohesion. We've got distribution. We're allowing components to run separate processes that can be deployed independently of each other. That's the key we want. That's that independent deployment. And we also basically have platform independence. We're no longer confined to a single language. All very good properties building large systems. Okay. The other weakness we discovered with kind of component-based architectures is that no one really addressed this problem of data. So we tended to end up with all these components operating still on one database. And the problem with that was, although each of my components is theoretically independently deployable, if we share write access to a given table, if one component alters the schema, all the other components need to get released at the same time. We had no rule which said, thou shalt not share the database. So I just wanted to review the other problem in a bit more depth about RPC, because one of the problems that I see in where people are doing microservices quite often today is that they are using RPC. We know RPC is a broken mechanism for doing that, so we should learn from history. Okay, so as well as basically this problem of fallacy distributed computing, so one of the problems there is there's this patterns called retry, circuit breaker, timeout. There's a really good book called Release It that you should probably go and read if you're doing any distributed software. We have to basically make sure that we observe the problem that when we're calling across a network, it's unreliable. But as well as that, there are other problems. We have this behavioral coupling. So the way I usually describe this is, if I say to you, if I say to Gary, I'd like a cup of tea, and I say, Gary, what I want you to do is go and fill the kettle with water, turn the kettle on, boil the water. When the water's boiled, pour it into my teapot which you've pre-warmed with my 3 tea bags, etc., etc. The problem becomes that I'm not letting Gary optimize for better ways of making tea. Gary has been following Heston Blumenthal on YouTube and knows that there are better ways of making tea. And he could make that for me, but if only the thing I changed was to say to Gary, make me a cup of tea, he could optimize for the best way to make tea. He could become the tea-making expert. I still get my tea, but I'm not giving instructions. And the problem with RPC is you tend to give instructions to the other side on how it should operate. So you constrain the range of implementations that it can produce, or if it chooses to have a better algorithm, it has to break you in order to basically force you to work in a new way. So it's better to be declarative. Ask for what you want. I want a cup of tea. Don't describe how that cup of tea should be given to you. This notion that we could essentially from an IDL, interface definition language, generate a proxy that would enable us to be language independent breaks very rapidly, because it's okay when languages are very similar, like, for example, .NET and Java, but it begins to break down when languages become more disparate, and you spend an enormous amount of time as a developer actually writing your own marshalling code inside your entry points into your application to swap given types around. Anyone who did kind of program between VB and C++ spent a lot of time dealing with string representations because, of course, they're different. And so that never turned out to be as good as we'd hoped. But to temporal coupling, so essentially the idea is, because I'm assuming that actually you exist and I'm not aware of quite often these fallacies distributed computing, my problem is that I can't get service out of you unless you are up. And that causes my uptime to be dependent on your uptime. And versioning is very hard, right? So anyone who's dealt with kind of classic component-based interfaces knows that you end up with, I-shipping algorithm 2, I-shipping algorithm 3, I-shipping algorithm 4, because you don't want to break your existing client, so you have to create new interfaces which your new clients can manage with your new improved algorithms. Gary's new improved tea-making method basically requires me to now actually call a different interface. Okay? And that gets really weird quite fast and becomes very confusing for developers because you're constantly navigating through this range of interfaces. So, how's this one doing? I need to zoom this one at the top. Guys, all right, can you read that? Let's zoom that one a little bit. All right. So, we come up with this incredible new idea, and that idea was to do service-oriented architectures. So up here, this component we have here is a service provider, and, oops, it's easy. Let's see if I can do that. Can't get any bigger. Okay, so the idea behind a service is we say, well, there's going to be an autonomous component. Well, that's kind of similar to what we had before, but we're going to have explicit boundaries. Now, what that means is we're going to say, well, look, we can solve this problem about data that we mentioned with the shared database by saying that we are going to hold our own data, and nobody else is going to be allowed to access our data, only us. You have to call us through our API or send us a message. It's the only way to get a change made to our data. Data lives with us, right? That solves the shared database problem because now I can truly deploy independently, because if I change my schema, I'm the only person that cares. You don't care. And a corollary to that is we don't share schema, and we share a schema messaging between us. We don't share types. So we avoid this problem of this kind of IDL notion. We say, well, rather than essentially depending on this kind of interface definition language to generate type structures, which may be very inconvenient, it's just essentially that XML or JSON as a message structure, and that's going to be much easier because you can interpret that text and choose to do what you will with it on the far side. Compatibility based on policy, generally that doesn't come up in this particular conversation, but that's around the fact saying that, hey, I want to be securable, let's use OAuth, and that helps us get around the fact that we're kind of network-based and distributable, right? So I want to be able to run anywhere. So we solve some of the component problems by being explicit about boundaries and saying we're not going to use IDL anymore, we're going to use some much more of a messaging approach. Okay, we'll come back to that latter point in a second. Same set of things we've got before: decoupled, highly decomposed, testable, highly cohesive, and interoperable. Okay, so because the sales the only problem is that early implementations were broken. So they used SOAP. SOAP was originally intended to be a IDL replacement for DCOM, because DCOM didn't work very well over ports. So SOAP was designed to basically be a way of accessing objects remotely over port 80. So the name is Simple Object Access Protocol, and things like WSDL are effectively just more IDL for generating types. And that didn't really work. So later on, people moved SOAP, SOA to use messaging. People even recommended using SOAP, what they call document literal syntax. But generally the move to SOA was to say, let's drop SOAP-based interaction and move towards a messaging-based interaction, REST, sending messages basically over message-oriented middleware. Okay. Major disadvantage is, well, we solved quite a few of the problems we have with components, but it's still worth being aware that we are a distributed system. And as soon as we are a distributed system, we increase our complexity. One of the key problems we tend to see is that people say, I no longer have an overview of what happens when the front-end user presses a button on the website and says, I want to, I don't know, ship between London and Oslo. It's now very difficult for someone to figure out, well, where does that actually go in the system? Because it comes in on my API, and then that raises messages which flow off to another system, which raises more messages in turn, which does its work. And QAs, other people get very panicky at first because they say, well, I need to write all these end-to-end tests, I need to understand the whole problem, and you're trying to convince them to work in a component way where essentially they say to them, this team, only need to understand how shipping rate calculations works. Your boundary is the boundary of shipping rate calculations exposed by your API. That's a contract. Provided that contract is satisfied, people can test that contract and prove that you call shipping rate calculations. You don't have to worry about your place in the overall system. And that, for some people, is a jolt which they don't like. But to look again at where we're going, so we're saying, hey, look, we're decomposing, we're doing loose coupling. Now we're effectively saying that our boundaries have to be explicit. There's no access to my internals, i.e. my data, right? So that the data was essentially a weak point for us, and we're now saying we protect that. We're cohesive, we're distributed, and we're platform independent, and actually we're independent now probably of host OSs much more as well. The idea behind SOA was it's much easier to basically have a .NET application talking to a Java application because it's XML right over HTTP, and that's straightforward. Okay, and even when we move to REST, it's JSON over or XML over HTTP, or you're firing it over message-oriented middleware, and you're choosing what your serialization format is in your message body. It may be JSON or XML, it may be something in protobuf, whatever. But you're very independent. Okay. It turns out that the vendors got hold of SOA and they created a few issues around the whole SOA idea. And SOA was flawed a little bit right from the outset. SOAP was a bad protocol choice for the API because it was very much an RPC-based protocol initially. And the second real flaw came with this, the Enterprise Service Bus. So we began to move away from SOAP. People said, well, you know, we can basically all communicate via messages. We've got some legacy systems on SOAP in our enterprise, and this whole thing is kind of a mess of old SOA services basically using SOAP, new things that ought to use messaging. How are we going to plug it together? And the vendors came along and said, don't worry, we have you covered. What you'll do is you'll plug it all into our ESB, and our ESB will take care of making one service talk to another and finding one service another and translating messages between different formats and finding the right version of a service. This is the key, they said, basically, to your SOA implementation. Lots of SOA implementations failed, right? And they actually failed probably because they were too ambitious. Organizations said, we must become SOA tomorrow. and the project got kicked off and abandoned halfway through because it reduced their business benefits. But the vendor said, oh no, the problem is you don't have any enterprise service bus. The enterprise service buses cause you problems, right? What happens is that they tend to basically put a whole load of logic into the bus. And one of the problems is there's things called process managers, where essentially I say, oh, you know what, actually my business process consists of my this app calling this app, this service calling this service, calling this service, calling this service. So, and if this happens, actually you should call this service. And slowly that logic begins to accrete into actual development. And suddenly you find yourself writing code in BizTalk, which is really untestable and a nightmare to live with, right? And anyone who's lived with BizTalk, it's very, very painful. And slowly what happens is the behavior of your application creeps out of your services and into your enterprise service bus. And you're now locked into this enterprise service bus because it comes from a vendor. It's not an open standard, so you have to keep paying them the money because your business is going to start failing now. And how do you get this stuff out? So the enterprise service bus implementations of SOA were also a significant problem. So, microservices. So microservices are really just, and I will do a zoom in a second for you, attempt to try and say, okay, we know that the best strategy that we think to actually solve the problem of complexity when we get sufficient numbers of lines of code, want to have multiple teams, and help our development organization to scale is to use components. But there have been problems with our component-based approaches, either the kind of DCOM, Corba, RPC-based family, or the SOAP-based kind of SOA or ASP-based family. So what's our next best attempt at doing components? Okay. Oops, sorry. Apologies. Okay. So I need to see what you can see. Okay, right. So microservices have the same property that they are components which essentially can run independently or can be deployed independently of each other. Right? That's a key definition of what we mean by a service. It's just a component that can run separate from other components, can be deployed separate from other components. So it's autonomous. That's the key first property. Second property is it has an explicit boundary to what it's before, right? Essentially, you have a stable interface, or there could be a messaging interface as much as it may be a actual kind of REST API. But there's some stable interface to which we basically talk to the contents of the service, right? And communication with the service is only through that interface. So again, we don't share data in the inside the service by any means. The database lives, if you have one, lives with that service, and so therefore the other services are not subject to schema change. You don't share databases. Okay, it's a bounded context. So given that we have our own set of data, our own model, the best way to basically pick the boundary size for your service is to look at something like DDD, which says, okay, a bounded context is a part of your domain problem that you're going to pick off, where you say some terms and language are in ubiquitous language are shared and are common and have a particular meaning, which may not be the meaning in another part of the business. And we pick a part of the problem domain, and which essentially is of a reasonable size, where we have meaning. So it's easiest to explain with an example. So I've worked in insurance, which is quite easy to explain about, where, for example, you have the notion of underwriting and claims. But the underwriting and claims have the notion of a policy, but they care about policy in different ways. In underwriting, they care about how much money they're going to charge you to give you that policy. In claims, they care about whether when you phone them up and say, I want to make a claim against my insurance, whether or not essentially that's a valid claim against that policy. Both have a notion, but a policy, but it's quite different in each context. And both of those represent different models of the universe. And if we want to model underwriting and claims separately, we don't want to share that concept. We may want to communicate about it as a shared cognate, but within that bounded context, it has meaning, but not across the bounded contexts. Right? So the next thing on the list is, whoops-a-daisy, sorry about that. Let me do that again. It's a business capability. So what's an appropriate area for me to pick a bounded context? What's an appropriate problem space to model? Generally, you want to look to how the business divides itself up. The business will divide itself up into a number of capabilities already, which are things the business can do and considers to have a particular skill set, a particular body of knowledge. It has domain experts in. So if you go look at an insurance company, there's a claims team who's entirely separate from an underwriting team, probably entirely separate from a team that handles the submission process. And those are good boundaries to think about. And generally, those teams internally will share their own language, which is the language you want to capture the domain model, which may not be the same language that other teams are using. So you're looking at business capability. Microservices tend to be eventually consistent. Well, a little bit, but generally the idea being that if I'm making synchronous calls between two components, the uptime of component A depends upon the uptime of component B. It's much easier when you're building scalable systems to avoid that problem we were talking about earlier in kind of RPC by saying, I'm going to send you a message and you're going to respond to it at some time, but there may be a delay. So I'll accept eventual consistency between services to get over this RPC problem of I'm assuming that this is reliable, fast, no latency network between my two components. Decentralized governance. So this is merely the DevOps movement having its influence on how we begin to think about deploying stuff and saying this notion of you build it, you own it, right? Given my team essentially is organized around shipping this particular component, then rather than them punting that over the fence to the maintenance team, they should just continue to own that particular service. It's got a nice boundary, work on it, maintain it, fix operational problems around it, and take it forward. And that's a really valuable way of keeping those services alive and healthy, because if the team has to basically do PagerDuty for its service, it will quite happily fix the problems. If somebody else does PagerDuty on the service, they won't. And this is also quite often referred to as embracing Conway's Law, in the sense that Conway's Law says that your architecture will tend to reflect the organizational structure that built it. So what you should do is actually say, organize my development structure around my architecture. So organize teams around individual components such that those teams will have to be forced to go and communicate with each other by agreeing contracts. If you don't do that, and teams can basically follow features across the whole range of your services, they will optimize for the features and tend to basically collapse your boundaries again into a monolith. And that's this idea also down below, effectively saying consumer-driven contracts. Okay. Properties, most ones you've seen before, testable, cohesive, interoperable. Decentralized governance is a new property here. And this notion here called smart endpoints and dumb pipes. So the idea says we should basically, when we communicate between two services, never use something like enterprise service bus. We want dumb communications. So we want basically just to send something over HTTP or TCP between two services, or we want to use a broker, a lightweight broker like a RabbitMQ, which is not building this kind of like process manager enterprise service bus functionality in, but it's simply a way of two components sending a message to each other. Okay. And so focus essentially away from enterprise service bus driven architectures. Disadvantages, again, same problem before. Complexity of a large number of services means it's more difficult to reason about what's happening. Okay. And then we look at the principles we're following. We can kind of see that we've added a few. So when we talk about decomposition, we're saying we want to basically pick business capabilities and create a bounded context, i.e. try and model that domain problem, the problem of that particular business capability within one of our services. And we're saying that on our cohesion, we want to basically provide, it's probably a complex problem, but we want to basically have consumer-defined contracts so that the consumers of your service have an influence on the design of your contract to avoid you just abusing them by saying, well, I'm going to change a new version, tough guys. And distribution. So essentially here we're saying you own it, you build it, you own it. All right? But you can see that the idea behind microservices is not particularly anything new. You've been essentially, you have, from the day you started building, main and subroutine, objects, layered systems, you've been applying the principles of microservice decomposition, of loose coupling, of abstraction behind an interface, etc. already. You understand the principles that you're using here. We're just pushing it up when we have multiple teams or large numbers of lines of code or software to the point where we can break it up into units which are independently deployable so that we can essentially solve the problem of not having everyone playing in the same sandpit. Okay. When I was a kid, I used to love the wet sandpit. I hated the dry sandpit, but they only let you have two of you playing in the wet sandpit at any one time. What they needed were more wet sandpits but the nursery teacher didn't sort of work out the solution to that problem. I could revolutionise education, more wet sandpits. Right. You can get carried away. So one of the problems with microservices in conversation is, what is a microservice? What does this word micro mean? Micro implies small, right? So these must be really small. And you can see various pieces of literature out there, people saying, oh, it's 50 to 100 lines. Oh, it's less than 1,000 lines. Okay. Lines of code are a really bad metric for a service. What you want trying to do is model the problem space that the application is going into. So what you need to do is identify suitable business capabilities which map to separate domain concerns that your business has. Insurance is a good example because it's very segregated. So you've got basically the actuaries that deal with rating. You've got basically the underwriters which deal with basically assessing risk. You've got the claims team which deal with reducing our losses. Those people have their own domains, their own business processes. They are capabilities that probably want their own service and should be modelled. And it's about picking those off. Now, once you get some of those more coarse-grained ones that get out of the domain, you may find within basically the underwriting process or the claims process there are actually a couple of different teams that do different things, which would be a good model of business capability, and you have to figure that out from your business. But it's about modelling the problem space, not picking a certain number of lines of code as your arbitrary target for the number of services that you need. Now, that said, there are some advantages on more services than less services. And we'll talk about those in a little bit as to why the trend is to push down from. So if you have something like underwriting, why you might want to look lower than underwriting. I'll come back to that a little bit. But what I want to talk about is this problem which comes from SOA called nanoservices. The problem becomes is if I break up things too much, I get a number of feature problems. The first is that, let's say my underwriting is separated up into kind of, something that says, this is my bit where I customer address entry service and insured location entry service and insured name service. And I've got all these, a given page takes 20 services because each one is doing like a function, essentially. The problem with that is I'm going to get very poor performance because that represents a whole series of calls between services. If I'm doing, say, for example, HTTP API calls between my services, the latency on that is going to accumulate. If I'm doing eventual consistency by doing messaging, that's going to accumulate. So the performance goes down with the number of services I introduce. Okay? My logic could be very fragmented. If I pick my boundary wrong, then rather than a team being able to say, okay, we need to add this product feature to our service, for example, being able to rate, car insurance policies, and we go to our service and basically do the work to basically implement that, we have to basically go and change 30 services. And we have to coordinate the effort across 30 service changes, which are probably owned by individuals. And that coordination effort is problematic, and the fragmented logic is problematic because no one can get an oversight of what happens. Okay. And the final problem with nanoservices essentially is overhead. Every service has an overhead to develop, every framework you use. So if you're basically building a Windows service, for example, even using top shelf, every service has basically an overhead that you've basically got to pay. And management of more things costs you more, right? On the other side, if we have a monolithic application, we get some problems. Poor modifiability, so these things essentially are problematic because we've got multiple teams trying to alter the same service, and they've got lots of shared data and shared dependencies, so it becomes very difficult for them to move forward. They tend to have basically problems of releasing because actually what happens is we work for a few iterations together and then we try and fix all the problems we've had from multiple teams working in the software. We have a long release hardening window of a couple of weeks long where effectively we try and fix the issues. So you've got lots of stored value which is not being released to customer bases. And one of the problems in monoliths is it's much easier to add something to the monolith than it is to do anything else. So they accrete complexity because it's much easier to keep going with your monolith than to fight it and break it into services. And there are no new platforms, right? I'm baked into .NET running against my SQL Server because that's what I've got so far. If I wanted to use Go because I felt very trendy, I'm out of luck. Not going to happen. So somewhere in between is kind of a Goldilocks service. right? This idea essentially, if it's not too big and it's not too small, and that's where microservices are, but it's really hard to put a specific number on it because it's domain dependent. Okay, implementing microservices. We're going to go a bit faster. Right. So remember with architectural styles, it's turtles all the way down. So the idea effectively is that any style can be decomposed. So a service might be decomposed into some layers and some objects, or effectively a procedural code underneath. A small service could actually just be a service with a main and subroutine, right? Procedural programming is not dead, it's useful for small numbers of lines of code, right? So now I've broken my problem up to units that are below 50,000 lines of code. Some of them might be 2,000 lines of code, and some of them might be best solved with main and subroutine. Okay. The other thing is, actually, the one that always confuses people is my service might actually consist of multiple components. So service is a logical boundary. It has certain properties, which means it's autonomous, but I could actually have multiple components. By that I mean I could have an IIS endpoint and a Windows service, both within my service boundary. So borrowing from Udi Zahan, we would distinguish between basically a business capability, something that's basically a service maps to that says I offer some service the business understands, and a set of autonomous components inside it that actually say these are individual schedulable units as far as the operating system is concerned. That's a physical deployment concern. It's not a concern essentially of the service boundary. Service boundary is logical, whereas this is actually a physical deployment boundary. I'm saying I can optimize my service by splitting it into these parts. These parts can access the same database, share the schema, they are coupled together, and they are released as a unit, right? Because they are parts, they form the same CI boundary, they're part of the same bounded context, they share the same model, and therefore they all have to release together. But it's a physical distribution optimization for performance reasons or whatever. Okay. So how do services talk to each other? So essentially you can do HTTP or TCP calls. It's very simple. Service A calls service B via an HTTP call port 80. You do OWIN self-host inside your Windows service, or you use Netty, as common in the Java world. You could use Helios out of the Akka.NET project. You want to be really fast on .NET. But essentially you're making a call. Thing to avoid, try and avoid basically slipping into the bad old RPC world of saying fill the kettle with water, put the kettle on to boil. Just say I want a cup of tea and try and basically work at that level. REST is helpful here because REST tends to work much more at that level, right? That's one of the reasons why you might use REST. So you might want to use REST. This is REST architectural style definition. You can be asynchronous. You effectively use a process of effectively returning a 202, which says I've accepted the request, and provides some mechanism for the call to monitor, and it may be better than basically waiting for a while for long calls. And you can use some kind of event-driven architectures using things like Atom. Okay. My preference, because the problem with that prior item means that you have to worry about things like, well, is the other side up? If it's not up, what about service discovery? How do I discover new instances? I need to start running something like Console or Zookeeper to discover services. I need to run something like Console to make sure services got a health check monitor. I start new instances. It's actually something with a broker in between. Use a lightweight broker like RabbitMQ and use events. The service A simply says, I'm going to raise an event, and service B and C are listening for events. And that's how we communicate between services. Okay. So my reservation system at the hotel raises an event to say Ian has booked a hotel room, and the billing system basically is listening for those events, and then it tries to basically build the credit card details that I gave. And if that fails, it raises an event saying Ian's booking failed, and that goes back to the reservation system, which picks it up and sends me an email saying you ain't staying with us. Okay. Breaking up a monolith, how do we do it? Okay. So I have a monolith and I want to basically turn it into service. So what's the easiest way of doing it? Okay, so what you want to do is identify what represents a business capability inside your system that you're going to break out. You basically, the simplest thing to do is to cut and shunt that into a new project and say, here is my new service, right? Generally don't start by rewriting, because that's an inglorious way towards death. Start by essentially taking the existing code and refactor it, right? You may do some initial refactoring here because you may want to basically solve some problems around things like poor layering, etc. So it's an opportunity to do a little bit of refactoring. Okay. What you want to do, once you've done that, is something called asset capture. So your goal is to own your own data, and to basically say all access to your own data must come through here, and my model is independent, I can be released autonomously. So asset capture says all the rights need to come through me, through my interface. So generally, you might do something like, for example, where we commonly do it is build a new user interface, nice, fresh, clean one, and actually get it to call the API. And slowly, all the writes start coming through to this system, not to this system. Right now, they may well be sharing tables in the database, so you have to watch for that in the initial process around the fact that it changes here, flag changes here. But you begin to, over time, capture all the assets. Okay. You then want to use something called event interception. So event interception says, well, I may have things over here where I want to be able to read some data that actually other parts of the monolith refer to. And rather than essentially making HTTP API calls across here, what I'm actually going to do is, because most of this is a shared collection, is take advantage of this idea of data on the inside, data on the outside, and which is from Pat Allen, which is I can have copies of shared data. So commonly things like customers, employees. I have a copy. I don't write to it. I just use it basically to complete operations. It's read-only as far as I'm concerned, and immutable and published out of here. We can event interception to say, right, well, either capture by triggers on these tables, publish events, as though this thing was actually event publishing, events to represent changes to that data. We tend to use scraping an audit trail. We scrape the audit trail and we publish events as though those audit entries were basically things that had happened, and then we subscribe to the events over here and build our local caches of that data. That enables us to get control of the data over here. We now control writes to a whole set of tables, and we control reads from related tables. And that's what reference data, and that enables us to basically go towards autonomy, which says we can cut all the links at a certain point and say, actually, I have all the data I need in reference terms, and I now have all the rights, so I'm now independent, I can be released autonomously. That's one way of building a microservice from a monolith. The problem most people have is the shared data in the database. That is what holds them back. So you have to get into your strategy a way of essentially breaking that problem. It's worth reading Pat Allen's Data on the Outside versus Data on the Inside white paper if you want to understand how some of that strategy works. Okay. Operating microservices, we are close to time, so I think we're about right. Okay. The old world in which we basically used to release software looked a little bit like this. We'd have a planning game, whatever you want to call it, depending on your preferred flavor of Agile or whatever you're using, where we create a whole load of stories. A team would basically say, right, in this iteration, we're going to commit to a whole set of stories and work on stories in the iteration. They would then get to the end of the iteration, hopefully QA'd in the iteration, and then they'd say, oh, before we get this out the door, what we actually want to do is release hardening. So we'll basically have a window where essentially we begin to test everything and prove that it really works because the developers probably lied to us. And then post that, we'll actually go and swap it out. So we'll hand it over to the ops team because, we don't want developers touching production. And they'll basically go and actually probably copy and replace the new code in and, stop services and restart them. The trouble with this process is an exceptionally expensive way of getting your software out the door. And increasingly, if you are in, say, for example, the software as a service market, table stakes is no longer that. Table stakes is, I build a story. The team basically gets a story off the backlog. They get one story, they implement it, and they press a button and they release it. Okay, and that is the model you need to be striving for, or you will not be competitive. Okay. So there's an advantage of us doing that. So if we have autonomous components that are small, belong to a team, and we have a you build it, you own it model, it's very possible for us to actually get to the world where the team says, okay, we can take responsibility for both deploying the service and owning it in production. You may have some regulatory requirements, which mean we have one of those, which means actually the ops guy has to be invited over to press the magic button. But you can work around that. He said to press the magic button. You can do all the rest of the work, and that essentially gives you the ability to move very rapidly. Now, as well as the business advantages of moving rapidly, there are some other advantages that you get. One of them is essentially your tolerance for risk increases. So remember that nasty release hardening period. The way you begin to eliminate that is if I can just push a button and do a release at any time, and my services of a sufficiently small size that the number of changes going in means I've only changed, for one story, 300 lines of code, then it should be possible for me to find defects in that code quite fast in production, or to have a feature switch means I can turn it on or off. So maybe I'm actually more comfortable about deploying without a long release hardening phase, because in the event I deploy out to production and it doesn't work, I just redeploy the old code, or I decide I can live with it and fix it and release a new version very rapidly. So you just turn that around much faster. And as your comfort for risk begins to basically increase, you may also become more comfortable releasing new technology stacks into production without doing, weeks and weeks and weeks of testing and deploying on trial versions and just changing a small bit of the application, because now, in theory, essentially, our ability to rapidly deploy out is much better. We may be comfortable that there may be some configuration issue we didn't expect. We can fix it quite fast. So rapid deployment increases your appetite for risk, because you have increased comfort that you can actually react to problems by simply redeploying out the code base. Okay. And that tends to mean you're more comfortable with technological change because you're more comfortable with risk. Okay. One last slide. Microservices cause you a problem, though, in the sense that now the teams are managing them, you've got lots more things to monitor, so that doesn't really scale very well if you've got 2 ops guys, right? Effectively, you've been traditionally able to look after the monolithic application. How are these guys going to manage all that? Well, you can push the problem out to the developers, and that's okay, but the developers tend to not want to basically do stuff manually anyway, so they're going to want to basically look to tooling-based solutions to try and make that problem a lot easier to solve. There's diagrams from Adrian Cockcroft, who's at Netflix, and he basically says, you have to think about these things: tooling, configuration, discovery, routing, and observability. So let's talk about those now. Observability. So one of the advantage things you might want to do if you're pushing services out rapidly and you're being more risk tolerant is to monitor. So one of the things in distributed services is you cannot predict via QA all the problems that you will get. So an easier solution is to basically say, I will do my best effort to predict them, and then I will need to basically think about monitoring recovery. Be aware that an incident is happening and understand how I will recover from it as soon as possible. And so things like, for example, New Relic, which is one we use, Logstash, so you can basically examine your logs, are really valuable tools for being able to see what's happening in your system at real time. Hystrix, which basically comes from Netflix, basically gives lots of windows into what's happening. Right. So I work on an analysis project called Brighter, where we're looking at that particular model. Routings, that's basically really turns out to be, each individual service has basically a small amount of framework, which basically you use to make sure that essentially it can receive messages. Things like Netty, we got for .NET, we got one called Brighter, basically, which we produce. You can go and find that on GitHub. Helios is very fast. Helios.io, very fast. And the Act.NET guys, version Netty for .NET. So discovery. So I need to discover services, right? So we've got a lot of services. I need to know where they are. I could just hard code those things into configuration files. That's a pain in the ass to administer. It's much better to have a notion of zero configuration. My services basically register and can be discovered. You may want to think about things like console. That uses essentially DNSSD. So basically that's service discovery, RFC for DNS. You can go and read about that. Things like Zookeeper effectively do that same job as well. You may want to then think about configuration itself using things like Zookeeper and console. So the ability to actually register with a database, essentially configuration properties that will survive essentially things like network partitions. Okay, and you may want tooling around your ability to actually deploy stuff out. So Octopus, Azure Resource Manager, Asgard, which comes from Netflix for AWS. All of those things help you essentially scale to meet the challenges of the fact that you're now running large numbers of services and you're asking basically the development team to manage that process. This is kind of less important, but obviously those are part of the mix that you will have. Okay. All right. That's kind of it. But hopefully what you can see in summary is you know how to build microservices. You've been using those approaches to basically decomposing large problems into smaller pieces. You just need to understand some of the learnings that have gone on in software architecture that when you go past about 50,000 lines of code or more than one team, you need to start thinking about componentization. And we have a significant body of knowledge based on experience with basically distributed objects and SOA. The microservices banner is essentially trying to provide a new best practice around component architectures. Okay, thanks very much.